Hi, it's Mr. Anderson, and this is AP Physics Essentials video 120. It's on the refraction of light, or the bending of light. And you can see in this picture here, there's a lot of bent light going on. And so what really happens, if we look at a laser light, as it moves through the air, you can see there's no refraction of light, or bending of light. But once it hits this glass surface, there's a bending of the light. Now, there's a little bit of reflection off the surface, but there's a lot of refraction or bent transmitted light like this. And the reason it's bending is because we're changing the speed at which it's moving through the medium. And I'll give you an analogy that's going to help you in a little bit. What would happen if we go straight into the medium? It's just going to go straight through. And so if you look on the glass to the left, the light that's coming straight through the middle where the surface is flat, it's not being refracted at all. It's only on that bent surface where we see that major refraction. And so when light moves from one medium to another, it can be reflected, absorbed, or transmitted. Now in this video, we're dealing with light that is transmitted into that other medium. Now in this example, however, the light came in at a straight angle, and so we don't see that refraction. But what happens if it comes in at an angle that is not along the normal or not along the perpendicular? And so these are the two mediums. This is the one on the left and the one on the right. This would be the boundary between the two, and then this is the normal line right here. And so what happens if it comes in from one medium, enters another medium where it's going the same exact speed? There's going to be no change in the angle. It's just going to go straight through. Just like light goes straight in air because the medium is never changing. What happens, however, if it goes from one medium to another, and that second medium, it actually travels slower? As it does that, it'll actually bend towards the normal, or it's going to bend towards that dotted line or the perpendicular line. I'll give you an analogy that'll help you to remember that. What happens if it comes in and it's moving into a faster medium? It'll actually bend away from that normal. So it's going to bend like that. Now that's called refraction, where you see the bending of the light, and we can actually quantify that using something called Snell's law. Snell's law, to quantify it, we have to add a couple of different variables. We first of all have to define this as the angle of incidence and this as the angle of refraction. Again, we're always measuring the angle between the normal and the light ray itself. And then we have N1 and N2. So this is what the formula for Snell's law looks like. And so the index of refraction, we call that N1, on one side times the sine of the angle equals the index of refraction on the other side times the sine of the angle of refraction on the other side. And so we can actually figure out what angle it's going to bend at if we know a little bit about the speed at which it's going through. And we also, if we see the bend, we could figure out the speed at which it's going through as well, because the index of refraction is equal to the speed of light divided by the velocity. Now, if we take that angle and we start to increase it, increase the angle of incidence, we eventually can reach what's called a critical angle. And instead of being refracted, it will not be refracted. It'll just go straight along the margin. And if we increase it above the critical angle, then it's going to be reflected into that first medium. And so what happens is eventually, if you get the angle right, you'll have total internal reflection. None of it is being refracted or transmitted through that boundary. And so let's get to that analogy I was talking about a second ago. And so imagine we have a marching band that's all walking together. And so we're looking at the marching band, the trumpet players, and we're looking at them from above. And as they're marching, they're trying to keep the space between them the same. So to the person to your left or the person to your right, we want to keep that exactly the same. And so imagine that they're marching down a road. You can see that they're going to keep that spacing between them the same. But let's say that there's a bunch of sand in the road. And so what's going to happen to their speed as they enter into the sand? Well, the ones that enter into the sand first are going to slow down. But since they kept that distance between them the same, you can see that the angle at which we came in equals the angle at which we came out. So we don't see that refraction going on. But now let's set it up so they're marching in at an angle like this. And so they're marching across, let's say, a parking lot, and they're going to hit some sand as well. So what happens is as they come in, which one is going to start to slow down first? Well, it's going to be this one right here. They're still going to keep this distance between all of them the same. And so watch what happens as they enter into the sand. You can see they're bending like that. And so we're going from a medium where it's faster to one where it's slower. So if I put in that normal right here, what happened? This is our angle of incidence, so it's big. what happens to our angle of refraction? It's going to be small. In other words, it's approaching that normal. And so you always, when you're looking at problems with refraction, you want to imagine that marching band in your head and figure out which way it's going to go. So let's try that again. We've got a marching band now going through sand, and they're going to come out into an area where they go faster. So they're all going slow, but they're going in a straight line. Now which one's going to start to go faster first? Well, it's going to be this one right here. They're keeping the distance between them all the same, and so watch what happens now. So it's bending like that. And so if we put in that normal again, our angle is actually increasing. Our angle of refraction is going to be bigger. Let's try to apply that with a prism. Let's say that we have a light ray coming into a prism like this, and inside the prism the light goes slower. So in the glass it's going to go at a slower rate. And so what's going to happen as the marching band approaches, try to figure this out in your head. I can see that the right side is going to start to slow down first. And so if that doesn't work, you could just memorize, put in the normal, and then figure out what happens to our angle of incidence and angle of refraction. But it's going to bend to the right like that. What happens if we go to the next one? So which side of the marching band is going to start to accelerate first as we move out? It's going to be the left side. If that doesn't work, again, you could put in the normal, and we could say that we're going to see an increase in that angle of refraction, or it's going to bend like that. Now we could even make sure that that's right. And so this is a PHET simulation. You can shoot a laser at different prisms. So if I turn the laser light on, we can see that refraction occurring. And once you figure out this analogy, it works really well. So in other words, what's going to happen if we shine a light right at a sphere, and we're going to try to hit it right along the normal. So it's hitting it flat. What should happen to the refraction? Let's try it. You can see it's not lined up perfectly, but it's going to go straight through. Let's try another one. What's going to happen here if we hit it at an angle like this? Where is going to be the bend? And so which one's going to start to slow down first? I would say the marching band, put yourself in that position, but the marching band on the right side is going to slow up first. What's going to happen as we bend, as we come out here? Try to figure it out in your head, but this is what it would look like. So we're going to get refraction that looks like that. And so you can see the more I get that bend, the more refraction. Or I could go in the other direction. That's why we could hold this sphere up, and if we look at it, the light coming from the other side is getting inverted. It's turning upside down due to the refraction of the light coming through. Now let's quantify a little bit. So we're going to use Snell's law in a PHET simulation. Remember, the index of refraction times sine of the angle of incidence, how it comes in, equals the index of refraction on the other side. And so index of refraction, remember, is related to the velocity. And so the index of refraction goes up as the velocity decreases. So let's take a look at this. So we've got a laser light bouncing off the surface, and so you can see there's a lot of reflection going on, but a lot of that light is also going to be refracted on the surface. And so in this problem, if you know the angle at which it comes in, could you figure out the angle of refraction? You need Snell's law to do that. And so I'd write it out like this, and then let me look at what information I have. So I have the angle at which it's coming in, so that's a given. I also know in air the index of refraction is 1. I'm also given the index of refraction of the surface down here, the glass, is 1.5. And so what am I really trying to solve for? I want to figure out that angle of refraction, how it comes out. So that's going to be my theta 2. So I plug in what I know. So this is index of refraction of the light, the angle coming in, index of refraction of the glass, and this is the angle coming out. So I solve for that. Now I've got sine of theta 2 equals 0.577, so I have to take the inverse sine to figure out what that angle is going to be, and so I get around 35 degrees. And so you may want to pause the video and make sure that you get an answer that's similar to that. And now we could remove the question mark, and you can see that that angle is going to be at 35 degrees. Also, you can see it's less, and the reason it's less is we're going from an area where it's faster to an area where it's going to be slower. Now you could also have the problem presented like this. So in this problem, what am I giving you? I'm giving you the actual refraction. So it's coming in at an angle of 60 degrees. You can see that the angle of refraction is going to be 20 degrees. And so could you figure out the index of refraction? Same thing, we're going to use Snell's law, and now you just have that one known, or those three knowns, and the one unknown that we don't have is going to be N2. Now what's interesting is if we look at material moving from an area of slow to fast, it would look like this. As we turn the angle, you can see that we're getting more refraction. But as we keep turning the angle more and more and more, you can see that less of that light is being refracted or making its way through. And eventually what we approach is something called the critical angle. Once we reach the critical angle, then we don't get light being transmitted into that next surface. And so what eventually happens is it's reflected back into this original medium. Now when all of it gets returned back into the medium, we call that total internal reflection. And so if we look at this sea turtle right here, the reason you're seeing its reflection up here on the surface is that light isn't moving out. It's being reflected to you because of the angle at which you're looking at that turtle. And so did you describe models of light traveling from one boundary into another when the speed of propagation changes? Could you find the relationship using Snell's law? And then finally, could you make predictions? The go-to analogy is that marching band analogy. Remember, they're going to keep the distance between them the same, but depending on which one starts to speed up or slow down first, we're going to get that refraction, and I hope that was helpful.